we watch the whole video at the very end, I'm going to tell you all the answers. And just have the thing turn off right at the last second. I'd like to see the looks on everybody's faces. So anyway, so yeah, so looking at this, so you have a positive thing is squared here, but you are multiplying that by t, which is on a negative stretch of interval, on a negative interval, -1 to 0. This is less than 0. This is less than 0 since t is going to be running in that negative interval from -1 to 0. So A fails. A fails, and so the answer here then is no, not a valid inner product. And that example kind of shows you that. Okay, so this is axiom A is very often the one that gets you in trouble. By the way, if I change the limits of the integral, if I integrate from 2 to 3, or anything positive here, right? If my interval is positive, then I would have been fine. Or if I had done this, t squared, then I would have been fine, right? So there's lots of ways to fix it. But if I just have that t there on this negative interval, then I know that this function is less than just this part right here is less than 0, and so therefore it adds up to a negative integration. Make sense? So what are the things you need to be able to do in this inner product material? You need to know these axioms, and you need to be able to run through a verification, whether it's yes or no on a question like this. This is a good, I think I've asked this question before, actually. So something like this, that's one thing. You need to be able to compute norms and angles and inner products in a particular example. And then the Graham-Schmidt process, which is really just using the formulas to come up with an orthogonal set to replace the vectors that I give you. Those are kind of the things you need to be able to do there. Does this make sense? You okay with that? Okay. Is there anything else anybody wants to ask me on chapter 4? I'm going to give you guys a choice. I would be happy, so there's a couple problems on here from chapter 5, the 5.1 stuff, which I haven't lectured on yet. Some of you maybe have looked at that video that I put up, and some of you haven't necessarily. Would you like me to go ahead, and because I have time, I'd be happy, I know it's already 8 o'clock, if you guys would rather just wait for tomorrow to go through this stuff, that's fine. But I would be happy to talk for, I don't know, maybe 15 more minutes on the 5.1 stuff and maybe do a problem or two. It's kind of up to you guys. Would it be helpful to start on that tonight, or are we just too tired to think about anything? My review sessions, they used to be so legendary. Like, I would go for hours and hours and hours. I think I said this before, the last time we did a review. And nobody would leave because, oh, he's going to say something really important right the minute I walk out the door. So people would just keep sticking around, and then I realized that all they really wanted me to do was shut up so that they could go home. And I thought I was doing them a favor by like showing them all these problems, and we went, no, I don't want to see any more problems. I just want you to stop talking about stuff. So I kind of, at some point, I decided, well, maybe this isn't what they want. So it's kind of up to you. I can go either way. I'm happy to, I will stay, as much as you guys want. If you'd like me to show you something, all you have to do is say something. You'd like to see something? Great. All right. We have a decision made. I'm going to talk briefly about 5.1. Okay. So let me just do it right here. And this is probably not a bad idea. That way you have a chance to kind of get on top of it early. So I'm just going to do it in the context of an example here. So I'm up to number 7. This is on the review packet. So let t be a function from P2 of R mapping to P2 of R via T of P of X equals x times p prime of x plus 2 times p double prime of x. Okay. And then the question is going to say, show that t is a linear transformation. Show that t is a linear transformation. Okay, so let's try this. On these problems, I have to give you all of this stuff. This has to be given, right? You're not supposed to know that in advance. I have to tell you, basically in general, what you're going to have is two vector spaces. Now in this problem, they happen to be the same vector space on both sides. But this is really just functions. You're just going, it's like drawing a picture of a function. Inputs and outputs. Okay? So we're looking at two vector spaces with inputs here and outputs here. In this problem, my inputs are coming from polynomials p2 of r. So I'm just writing it as p of x in this example. I could have written this as ax squared plus bx plus c. That would have been another way to write it. But I'm just going to write it as p of x right now. And then how do I come up with my output? See, I have to give you this. I made this up. And all I'm going to do is I'm going to take the derivative of the polynomial, multiply it by x, and add 2 times the second derivative of the polynomial to it. And I would like to show that that is a linear transformation. So I have to tell you, this is where the 5.1 comes in, because I have to tell you what it means that it's a linear transformation. So t is a linear transformation if, so t is linear. We sometimes just abbreviate and say t is linear. Just means a linear transformation if part A, t respects addition, and part B is going to be t respects scalar multiplication. Okay, so these two things. And let me just write what that means. It's very similar to closure under addition and closure under scalar multiplication. T respects addition just means that if I take t of v1 plus v2, so I'm doing addition here, I add two vectors, it should be the same as t of v1 plus t of v2. Okay, so we're just going to check if that's true or not for this example. And then the scalar multiplication is similar if I have a constant k times v. Scalar multiplication, I have to be able to pull out the k and have the same result. Okay? So this is the property, these two properties. So I bet we can do this. Let's try it for this example. Okay? So I have two things to check right here. I have two things I have to check to show that t is linear. Okay? So what I'm going to do is I'm going to say, we start off kind of with, we need to have two polynomials. Let's say p of x and q of x. Let's suppose that those are elements of p2 of r, which is what v is. Okay? What I have to do is I have to look at t, so I'm doing the first part, so I have to add those two vectors. So t of p of x plus q of x, right? So I take p of x plus q of x, and I want to transform the sum of those two vectors, right? That's what I have here. Okay, so what I need to do is apply the formula that I was given for t to this. So everywhere that I see a p of x up here in this formula, I now need to apply it to p of x plus q of x. Okay, so how's that going to look? Well, we have an x here times the derivative of whatever I plugged in, right? Well, the derivative of what I plugged in, what is the derivative of p of x plus q of x? Yeah, p of x prime plus q of x prime, exactly. Because you can, remember, derivatives respect addition, right? So I can just write that down. and then plus 2 times the second derivative of whatever I plugged in. What is the second derivative of p of x plus q of x? P double prime of x plus q double prime of x. Exactly. So this is just plugging it in. This is just plugging in p of x plus q of x into the formula that we were given. Everybody follow that? Now, what are we trying to do here? We're trying to show that t respects addition. So I need to, at the end of this calculation, get t of p of x separated from t of q of x. So would there be a good algebra step that I could do right now? If I want to get the p of x part separate from the q of x part, what might I want to do right now? Regroup and distribute the terms, right? Just do an algebra step. I'm going to put all of the p of x stuff together at the front. So I have x times p prime of x right here, right? But I also over here have plus 2 times p double prime of x. So I'm going to write that down. Okay, and then I'm going to put all of the q of x stuff at the end. So I have an x times q prime of x plus 2 times q double prime of x. Does that look all right? Okay. And if I look at that, I say, oh, the first part is just t of p of x, and the second part is just t of q of x. Right? So there you go. T respects addition. Does that make sense? Not too bad. Okay. Let's try the second part. T respects scalar multiplication. So this is part B. Here's the way I'm going to start it off. Let p of x be as above, and k is a real number constant. So it looks just like the closure under scalar multiplication that we did before. Okay. This time we're going to take t of k times p of x. Okay. And so what do we have to do? This is my input into that function there. So if we just read, how do we evaluate t? How do we transform this input? Well, we take x times the derivative of whatever I plugged in. So this is x times the derivative. I'm just going to put it like this: k times p of x with a big prime on the whole expression. So we're taking the derivative of that, and then plus 2 times the second derivative of whatever I plugged in. So that's k times p of x with 2 derivative signs on it. 2 derivatives on it. Okay? Now, taking a look at what is it I'm trying to come up with over here. At the end of this calculation, what do I want to have happen to the k? I want it totally out in front. So looking at what I have here, what would I be thinking about doing next?
Pulling out the k?
Yeah, can I do that? Do constants pull out of derivatives safely? Yeah, definitely, right? We've done that in calculus all the time. Constants pull out. So let's just pull the k right out of it. Out of everything, actually. Leaves me with x times p prime of x there. And the second part is going to be plus 2 times p double prime of x. Well, it's going to look like that. Okay? And what would be then the last line that I would need to write down? For the last step? K times t of p of x. Perfect. That's exactly what I wanted. So this is what 5.1 is about. Basically showing this kind of stuff. Does it make sense? Everybody good with that? Let me just give you another quick one that's not on the review sheet, and then maybe I'll show you one other type of problem that comes up, and then the rest of it we can kind of save for tomorrow. Just make things a little bit easier for you. Or you can watch my video tonight before bed. Something like that, I don't know. The video is actually pretty decent. Like, I actually re-watched it from a year ago. I said, man, I actually did okay with this. Because it's about a 30-minute thing, and it covers all the highlights pretty well. And it actually made sense to me 12 months after I did it. So, like, oh, that's nice. Okay, so here's another example. What number am I up to? 8 already. Okay, number 8. I'm going to define t. Let's go from m2 of r to r via t of a equals the determinant of a. Let's take this. And then the question is going to be, is t linear? Is t linear? Okay. Does it respect addition? And does it respect scalar multiplication? By the way, does it make sense that we should make sure everything makes sense here? If I plug in a 2 by 2 matrix, I can take the determinant of a square matrix and I get a real number. So notice my outputs are numbers. So this time my inputs are the 2 by 2 matrices and I'm outputting a number. This is just a function that takes a square matrix and spits out its determinant. So it's definitely a good function. The only question is, does it respect addition and scalar multiplication? So for example, would, well, let's just start trying part A. So let's just say, let's let capital A and capital B be elements of M2 of R. Now if I do T of A plus B, right? The question is that the same as T of A plus T of B? So let's see, this is the same, if I use the formula here, it's just the determinant of A plus B, right? Can I do anything with that? Determinant of A plus determinant of B. Is that right? If that's right, then we'll be very happy. We've looked at this before. It was a while ago, so I have to give you credit for the fact that before the first midterm we were looking at the... Remember that we went through a bunch of properties of determinants? Right, so here, let me give you an example. Suppose this was my matrix A, and suppose this was my matrix B. Right? So what's the determinant of A? 0. What's the determinant of B? But if I take A plus B, what matrix do I have here? The determinant of this one would be 1. So 1 does not equal 0 plus 0. This does not work. So we're going to have a problem here. Okay, it does not respect addition. Determinants do not respect addition. That's the point. Okay, so you can, when something fails, this is just like in the closure under addition thing. If it fails, you just need to give me an example that shows me that it doesn't work. So this would be a perfectly good example. T of A plus B for this example. So just this is A right here. This is B right. So maybe just write it as a separate example. So A is 1 0 0 0. B is 0 0 0 1. Right. So then T of A is 0. T of B is 0. But T of A plus B is 1. So you just tell me those facts, and that shows that T does not respect addition. The addition part does not work. So do I have to look at scalar multiplication? Not at all. This is all I would have to do. Okay? This makes some sense? Okay. One of the reasons why, I'm just make a quick little point about why these properties are important, and then do one last example, and then we'll call it. One of the reasons you want these two properties is is that you would like to be able to transform any linear combination. Oops. Right? If t is linear, then if you had an expression like this, these two properties, t respects addition and scalar multiplication, basically is going to allow you to bust this thing apart. Basically, you're going to be able to pull out the C1 and just transform V1. And then you're going to be able to pull out the C2 and just transform V2. And so on. So I'm kind of putting here, this expression is putting the addition and scalar multiplication together in a single linear combination. But using both of these properties allows me to get the t's separately applied to the vectors with the constants pulled out, right? So, in other words, you could actually just say in a single breath that t respects linear combinations, right? If it respects addition and it respects scalar multiplication, then if you just build a bigger expression that involves addition and scalar multiplication, and you just start using these properties, you'll be able to completely decompose it into this, right? Now, why would that be such an awesome thing to be able to do? Well, I'm going to give you one last example to show you why this is a cool thing. It basically means that if I tell you what t does to a small set of vectors, I'll be able to tell you what t does to any vector. And here's an example to show you that. So this is the last one for now, and then we'll pick this up again tomorrow. Suppose I have t, and it goes from p2 of r to m2 of r. And, so t goes from p2 of r to m2 of r. Let's suppose that this is linear. Let's assume it's linear. And then let's suppose I tell you that t of 1 is equal to the matrix -1, 2, 0, 0. And then let's suppose I tell you that t of x plus 1 is equal to -3, 0, 2, 1. And let's suppose I tell you that t of x squared plus x plus 1 is 3, -2, 0, 1. So I give you those three input-output combinations. Notice that I am inputting polynomials of degree 2 or less, and I'm outputting a 2 by 2 matrix for each of these cases. So now here's the question. Let's find t of ax squared plus bx plus c. Let's find that guy. This is, in other words, look what I'm just saying. I'm saying that if I just tell you t of these three things, we can actually find t of anything. Anything in P2 of R. This is an arbitrary element of P2 of R. So we're taking three pieces of information and generating infinite amounts of information about the whole transformation. That's what we're going to do here. Do you understand the question? We have inputs and we have outputs. I'm saying if I input this polynomial, this is my output. If I input this polynomial, this is my output. And if I input this polynomial, this is my output. And I made it up, and I'm just giving it to you. This thing. There's nothing, religious about this. This is just me dreaming in my sleep of my favorite numbers and putting it down. Just making something up. So this is what I'm saying. And based on that, this is what the powerful thing is. I can find t of anything if I just know these three things. And it comes back to this stuff over here, about the fact that you can use the linear properties of t to help you. For example, can I do anything with this? What can I do with this? How How can I rewrite it? My pen is ready to go. Right. That's it. That's it. That's it. Exactly. Now, that's great. That's great. Now, look, over here, let's look at the last term first. On the last term, look, I already told you what t of 1 is. It's just -1, 2, 0, 0. So you have c times that. Now, did I tell you what t of x is? I did not give you t of x, but did I give you something that you could figure it out from?
Plus 1. Plus 1.
This is t of x plus 1, and this is t of 1, right? So, you know what, guys? T of x can be thought of as t of -1 plus t of x plus 1. Remember, t respects addition. So if I combined these together into 1, it would just be t of x, right? And what is t of -1? Oh, I can pull the minus. It's a constant, right? I can pull it outside. So I actually do know what t of x is. T of x is just this one minus this one. Let's just see if we can start putting it down. So it's t of x plus 1 minus t of 1. In other words, it's this matrix minus this matrix. So I just have to take this one minus this one. So let's see if we can do this in our heads here. If I take -3 and I subtract -1, I get -2, don't I? -2, right? And if I take 0 and I subtract 2, I get another -2. And if I take 2 and I subtract 0, I get 2. And if I take 1 and I subtract 0, I get 1. Okay. Does that make sense, guys? Everybody follow what I'm doing here? Okay? This is assuming it's linear, right? I'm giving you in advance that it's linear. I'm trying to show you in this example the power of linearity. If something's linear, then I don't have to tell you very much information for you to be able to figure out this whole expression. What about t of x squared? How can I get that one? This one minus this one, right? If I take x squared plus x plus 1 and I subtract x plus 1, I'll just be left with x squared. So we just take this matrix minus this matrix. Okay, so let's see what that gives me. I have a times this matrix minus this matrix looks like it's going to be 6 and -2 and -2 and 0. You guys seeing that? I'm just doing it in my head slot by slot. 3 minus -3. -2 minus 0. 0 minus 2. And 1 minus 1. Those are my 4 numbers in this matrix. Okay? This would be a perfectly good final answer. Of course, if you wanted to, it would also be okay to just combine it into a single matrix now. So for example, the upper left corner would be 6a minus 2b minus c. That's the upper left corner. The upper right corner would be minus 2a minus 2b plus 2c. And then the lower left corner would be -2a plus 2b. And the lower right corner would just be b. Okay? So this would be your function. If I input ax squared plus bx plus c, I would output this 2 by 2 matrix. Isn't that amazing? We built up the entire function just by giving you 3 values only. And that's because ax squared plus bx plus c can be broken down into just these 3 particular terms. So that's a nice application of the linearity stuff. But most of the problems in section 5.1, they're just going to give you a capital T, and they're just going to ask you, is it linear or not? And you just have to check these 2 conditions here. And if they're both true, great. If one of them fails, give me an example.